This is the second session on the chapter Electromagnetic Waves, and here we are going to study about displacement current. So far, our notion of current says that if we have any cross-section area, if any charge is flowing in that cross-sectional area, across that cross-section area, let's say charge dq is flowing through that, in a time interval of dt, then current is simply nothing but the rate of transfer of this charge, which is dq by dt in this particular case. Also, if this particular cross-section is taken as the cross-section in a conducting wire, then this current is called a conduction current. Here in our topic, we have displacement current. So it's an entirely new and unrelated concept. To study this concept, we will follow a particular story, the story of how this particular concept was discovered in the first place. So the first piece of this story goes back to the Amperes Law. We studied Amperes Law. It helped us in calculating magnetic field due to a current. Specifically, what we said was, if we take any closed loop, let's say in this animation we have this closed loop, then if we want to find out this quantity called integral B dot dl over this entire loop, this quantity is also called the circulation of magnetic field, then it will be given by the formula mu naught times I, where I is the current that is piercing the surface bound by this closed loop. So this was what Ampere had said, and this came to be known as Amperes Law. Now there was another very important scientist whose name was Maxwell. He was studying about electromagnetic waves. What he did in one of his experiments was, he took a circuit in which he had only a capacitor. So now we will be studying about Maxwell's experiment. So in this experiment, we have this circuit in which we have a parallel plate capacitor that is connected to the circuit. Now, what Maxwell did was, he simply took a magnetic needle and placed it in the region between these two parallel plates. He saw that this magnetic needle deflected. This deflection indicated that there is a magnetic field present in the region between these two plates. Now, the next thing he took was, he took an Amperian loop inside this region. Let's say we have this loop, and then if we place our magnetic needles at all points of this loop, what we will see is there is a deflection in this magnetic needle at all the points. This indicates that for Maxwell's experiment, we have integral of B dot dl as some finite quantity. It's definitely not a zero quantity, it's a non-zero quantity. Let's denote it as k, and k is definitely not equal to 0. However, in this loop you can see that there is no current that is piercing the surface bound by this loop. So what you have is mu naught times I for this particular loop. This quantity is 0. So this was an inconsistency that he had discovered. For this particular loop that is placed in a region between two parallel plates of the parallel plate capacitor in a DC circuit, what he saw was that integral of B dot dl was not equal to mu naught times I. This experiment kind of violated the Amperes law, and Amperes law is a law. It needs to be true across every situation, across all the kind of experiments that we construct. However, in this particular experiment, he saw that this Amperes law was not valid. This stoked a kind of controversy, and scientists all around the world started thinking about this problem. What they were seeing was, whereas Amperes law was holding true for all other situations, it was not holding true in this particular situation. The answer to this question, why Amperes law was not valid here, it was found by Maxwell himself, and he kind of applied a series of logical train of thoughts to arrive at this answer. What he said was, first of all, he said that in this circuit that I have, let's say this is our circuit, these are two parallel plates. So in this circuit, he says, if I take an Amperean loop here in the region between these two plates, let's try to calculate the circulation of magnetic field, or this particular quantity, for magnetic field that has been produced due to the current. So of course, if B dash is the magnetic field due to the current that is flowing in this circuit, then what we get is B dash, which is the magnetic field due to the current, dot dl across this loop. This quantity is equal to mu naught times I, but I is 0 for this loop, so we get a 0 here. So the key insight that he derived out of this thought was that the magnetic field B that is produced in this loop must be due to something other than the current that can be flowing here. B is due to something else, not current. Then what he did was he started noting special things about this circuit. What else could be the cause of this magnetic field? Then one of the key observations that he made was that during the charging process, or the process when there is current set up in the circuit, because we know that for a DC circuit, after the capacitor has charged, there is no current at all, right? So during this charging process, he observed this special thing that the charge is accumulating over time on these parallel plates, and because charge is accumulating, or in other words changing across in these plates, the electric field due to the charge distribution here across these plates must also vary. So the key thing that he noticed here was that for this particular Amperean loop, the electric flux that is passing through this closed surface was not zero, it was constantly varying also. So if we denote the electric field by the formula Q upon epsilon A, then this quantity is varying because Q is varying. The last piece in the puzzle for him was the observation that was found in Faraday's law. In Faraday's law, we have already studied that EMF, which can also be written as, if you are talking about a closed loop such as this loop, the EMF can be written as E dot dl, with a minus sign of course. Then this particular quantity, he found out that it was equal to the magnetic flux that is passing through this loop. In fact, the rate of change of the magnetic flux that was passing through this loop, with a negative sign. So he observed that Faraday's law, this law states that due to varying magnetic flux across this loop, there is an integral E dot dl, or rather an electric field that has been set up at all points across this loop. He also observed that the electric field is changing this time for this particular loop because the capacitor is charging, hence its charge is varying. So he reasoned, if varying magnetic field can produce an electric field, why can't a varying electric field produce a magnetic field? So this was his key insight, and what he found out was that there was a magnetic field at every point on this loop, and that magnetic field was due to the varying electric field. So this was the equation that was given to us by Maxwell, and we treat it as a law because this was found out of experiments, and of course there was a lot of reasoning that was involved behind it. The expression that he gave was integral B dot dl across this closed loop. If we want to calculate it, it can be calculated as the formula mu naught epsilon naught d by dt of the electric flux across this loop. So this is the formula that Maxwell gave us. He said that this time the magnetic field that is produced at all the points on this loop, they are not produced due to currents, they are produced due to varying electric field. And then he gave us the relation between the circulation of the magnetic field, which is closed loop integration of B dot dl. It was equal to mu naught epsilon naught times the rate of change of flux through this particular loop.